Swayam Prabha. Digital India. Educated India.
Good morning, everyone. We're going to continue our discussion of integrated components for millimeter wave circuits. So in the prior lecture, we looked at inductors and capacitors. So we'll look at more distributed circuits for the first part of this class, and then we'll start talking about building phased array components using these circuits. So let's have a quick overview of transmission lines, and then we'll also consider integrated implementations and approximations for transmission lines using lumped circuits. So as we know, transmission lines are distributed circuits which are modeled using unit inductance, capacitance, resistance to in parallel with this, right? So there is so this is the model for one unit section, and we then repeat this model, right, to develop the model of our transmission lines. So why do we use them on chip? The advantage of building transmission lines are that they are well modeled at high frequencies. So because this is a distributed model, it's valid up to high frequencies. So it is compatible with high frequency / millimeter wave design. Since it is well modeled. And if we decide on a characteristic impedance, then we can break up our design by convenient design approach, where we can design our blocks to have output of Z0, and then we can interconnect blocks with the transmission line with characteristic impedance Z0, and then make sure that this block is matched to Z0, right? So by using this kind of impedance matching at the output and the input of different blocks and interconnecting them with Z0, what we can basically do is develop an approach which does not require these two blocks to be co-designed together. So later on, if we are physically separating these blocks and changing this transmission line distance, the impedance that we see here will still be Z0. So this block will perform as expected. Similarly, for this block, the source impedance will still be Z0. So this block will perform as expected. So it basically makes design at the block level convenient and systematic if we adopt a characteristic impedance and then design to it. Now in the external world, this Z0 is 50 ohms. There are some reasons for it as a balance between loss and an ability to handle power in the transmission lines. But this Z0 50 ohms doesn't come from any on-chip limitation. So it is quite possible for you to decide that inside your chip, the blocks will be matched to something different than 50 ohms. And if that is convenient, you can design. There are some limitations, which is that on the chip, having very high impedance transmission lines is challenging. So you can go up to 70, 80, 100 ohms, but if you're building really high impedance lines, that is challenging. And the second part is that when you interface with the outside world, then if you're interfacing with measurement equipment, etc., outside your chip, then that measurement world is still 50 ohms source impedance, for example. And then let's say that you're feeding this to a piece of equipment to analyze it, like a spectrum analyzer or network analyzer, that is typically 50 ohms as well, right? So when you're bringing your chip, then you have to consider being matched to 50 ohms, but it doesn't have to be necessarily matched to 50 ohms inside your chip. And of course, if you have full control of your system, for example, there is an antenna that is connected to your input, it is possible for you to design for different characteristic impedances so that the antenna and your block are both at that impedance, and then you can still have a matched design. So given this, we also know that for a transmission line, which is modeled like this with unit inductances, capacitances, resistances, and admittances, the Z0 is to be completely accurate. The Z0 is R plus j omega L divided by G plus j omega C, right? Which, assuming that we are in a situation where R is very small and G is very small, this we typically approximate to square root of L over C. So your unit inductance divided by your unit capacitance. And we can go through the math, but we can precisely define the propagation constant, which is alpha plus j beta, as G plus j omega C times R plus j omega L, right? And this basically the beta is the complex part of this, and alpha is the real part. So the assumption here is that as you have a transmission line, right, and signals are propagating on it, your forward and backward waves along the transmission line follow E0 gamma z plus V0 minus e to the power gamma z. What does this mean? This means that if I just take this forward wave alone, so V0 e to the power minus gamma z is V0 e to the power minus alpha z times. So what is happening here is that this magnitude of the wave, right, is getting attenuated as we travel down the line, and this represents the phase shift in the line or the delay in the line. So if I were to look at it graphically, what is happening is that I start with a wave that, let's say, looks like this, right? And then as z increases, I'm going to get a reduction in the amplitude, right, which is basically e to the power minus alpha z. So the wave is going to get smaller, right, and it is going to have a phase shift that is dependent upon beta z, right? You can define an effective wavelength of the in the transmission line, right? You can define an effective wavelength in the transmission line, which is 2 pi over beta, because if alpha was 0, right, then you can think about the distance in the transmission line that you have to go in order to get the same phase back. That is what a wavelength is. So you can see that the wavelength in the transmission line is 2 pi over beta. We can also now make some approximations here, right? So then we can basically see that alpha is approximately R over 2 Z0 plus G Z0 over 2, right? So depending upon which is the primary mode of loss in your system, one of these terms dominate, right? So if we were to think about, for example, a transmission line that we implement as a microstrip on a chip, right? So there is a signal, right? And then there is a ground plane below it, for example, right? So this would be the top view. And if we were to look at the side view, we are basically looking at a signal layer, right? And then underneath it, we have our ground layer. Right? And we are basically defining unit inductances, unit resistances, and then loss, and then capacitance, right? That's what this looks like for each section of this line. And if your dielectric is a very low loss dielectric, this G is going to be very small. If your metal has skin effect losses, for example, that we discussed yesterday, right? You'll find that this is a significant source of loss in the system. So it might be that this term sort of ends up dominating your losses, right? And beta itself, right? We can approximate it as omega square root LC, right? So this basically says that as I increase the product of my L and C, right? So as there's L and C are both getting larger and larger, then the wavelength of my line is getting shorter. Wavelength in my line is getting shorter and shorter, right? So if I want to have a short effective wavelength in my transmission line, I need to have high unit L and high unit C, right? And you can clearly see that beta and Z naught, right? I'll just write Z naught again, is square root of L over C. They are related, right? So if I try to change beta, and we will see later phase shifters that do that, then I have to be very careful because I might be changing Z naught as well, right? So given this sort of overview, we have some examples we've discussed before of integrated transmission lines, right? They are not very different from transmission lines that are implemented in MMICs or PCBs, right? So effectively, for example, you can have the microstrip that I just drew, right? So you have the ground layer, and then you have a signal layer, right? And right, so you're basically taking the signal with reference to this ground, right? So we call this a microstrip. And in the past, we've also discussed basically, so if we begin with what we call the coplanar waveguide, so basically you have a signal like this, right? And then you have the grounds in the same layer. So in the same layer, you have your ground lines, right? Right? So we can implement this on the chip, obviously, right? By putting the signal and ground layers on the same metal layer. And the impedance is controlled by the width of this line and the spacing of this ground to the ground, right? We can also build grounded CPW or CPWG, right, which coplanar waveguide, but grounded, right? So we do the exact same thing, and this is what we've been implementing, where we have the signal trace, we have the ground trace, and we add a set of BRs that take you to a lower metal layer, and we also implement ground in there, right? So this approach makes sure that we protect the waveguide from the substrate, and also it makes sure that there are no spurious modes that occur. So in this case, again, the impedance is set by the height that we have here, the spacing that we have here, and the width that we have over here. So these are all sort of single-ended lines, right? But we can also build on the chip. Many times we are interested in differential signals, right? So we can also build differential lines, right? And with differential lines, again, we have multiple options. We can build them as a microstrip, where we have the two signals and we have ground below. Or we can extend the CPWG structure, if we like, to a differential structure as well, where we apply. Right? So we can build differential lines like this, right? So clearly these lines can have common mode and differential mode impedances. We'll talk a little bit about this going forward. But again, here now you have a W, a space S1 between the lines, and a space S2 to the ground, right? You can also, of course, make a differential line by just putting another line here and then another ground plane. That's also possible, right? But this structure is usually more compact. So we like to use this structure. So in general, the lines, in order to keep them low loss, we implement them in the thicker metal layers, right? So we have multiple sources of loss here. So we have losses that are there in the conductor lines, right? We have loss that occurs in the dielectric. We might get losses that occur because of the fields coupling into the substrate, and also depending upon the kind of lines that we use and the frequencies at which we are operating, we might get radiation loss as well, right? So you can reduce this, for example, by making sure that the ground plane and the signal are very close together by not increasing it too much. You can do this by, okay, so you keep signals and grounds close, right? So that means S should be somewhat small relative to your wavelength, the frequency at which you're operating. Substrate losses, high resistivity substrate addresses this, right? And also the grounded CPW structures, right, which isolate the transmission line from the substrate. Then there is the dielectric loss. Unfortunately, you don't have too much control over this because it is what the foundry uses. But what really causes losses here in that dielectric region is the presence of metal fill, right? So you can basically do a lower density metal fill. And then to reduce your conductor losses, use wide lines, right? And also thicker metal layers, right? So these approaches get us to the point where we can on chip the kind of losses that we see are approximately 1 dB per millimeter, right? At 60 gigahertz, you can see losses that are of that nature. And if we then consider the wavelength, right? So effectively, what we see is if we around 2.4 millimeters, right, at 60 gigahertz is the lambda in the on-chip transmission line, lambda of on-chip transmission, yeah. Right? These are approximate numbers, right? I mean, they might vary a little bit depending upon what your technology is and how you do the metal fill and all that. But this starts giving you an idea of the order of magnitude wavelengths and loss that you can expect to get, right? Yes. Yeah. It will still work. So it will still work. We will discuss that context in the when we discuss couple lines, because differential lines are nothing but two lines that are coupled together. So we can talk about that when we invent this. But just to give you a very high level, if you don't have the ground, you are basically reducing the capacitance that each of these lines is seeing. So you're effectively increasing the impedance. So then if you want to maintain the same impedance, you have to move these closer together, right? So that's the kind of property that you'll have to adjust. There is one, actually before we discuss that, maybe we can take some examples of transmission line use, right? So let's say we know that when we have a transmission line, right, which is has a characteristic impedance Z naught, right, and has a wavelength that can be calculated from beta, and we have a physical length of the transmission line L, then if there is a load here that is ZL, right, this we know can be given by Zn is Z naught ZL plus J Z naught tan beta L divided by Z naught plus J ZL tan beta L, right? So what we then, many times what we want are impedance transformations, or we want to see, for example, when we were trying to discuss when we were trying to discuss transistor matching, we saw that if there is a certain load, we want to transform it to the optimum load that we want to see. So we see that the transmission lines can help us accomplish that. So we can basically control what Z naught and tan beta L is in order to transform a certain ZL to a certain Zn. Of course, in this case, there's only, by using just one transmission line, there's only a finite set of transformations possible, right? But we'll talk about more circuits with more transmission lines. But at its simplest, you can see that the transmission lines can help us translate impedances. This can be quite useful in some specific cases. For example, consider a case when ZL is 0, right? So then Zn is Z0 times Jz0 tan beta L divided by Z0, right? So it is nothing but just Jz0 tan beta L. And this is effectively, we see that it is an inductance, right? Because it's present in an imaginary impedance. And we can say that therefore, if I want a certain L, right, I can basically say that J omega L effective must be equal to Jz0 tan beta L. So I can decide, I can achieve a certain inductance by just using a transmission line of appropriate impedance and length at the frequency that I want. So practically, what does this mean? This means that we build the transmission line that we discussed. For example, just let's take a simple microstrip. We are just building the transmission line with a certain Z0 and a certain L, right? And right at the end of that, we are just putting a via and shorting it to this plane over here, right? So then when we look at the impedance over here, it looks like an inductance to us, right? So we might, in order to be very precise at millimeter wave, also just model this via, right? And that's the via is typically an inductance. So then we might build a little bit more complex model where we decide that we are terminating this in, let's say, 5 picohenry, right? That's the model of our via short. And then we decide, okay, Z0 beta, right? And we want to get the Zn that looks close to an inductance, right? So we can build circuits like that. Similarly, if we can show that if ZL is infinity, right? Or basically we have an open transmission line, then the Zn that we get is Z0 divided by J tan beta L, right? So this is effectively a capacitance, right? So I can get a capacitance that I want by having an open transmission line. So people will call this shorted or open stubs, right? Where we are leaving the termination of that line in what we want. And in a very useful transformation, we see that Zn is Z0 ZL, sorry, not the ZL, right? And in this scenario, right, let's say that we are terminating ZL in some impedance Z1, right? And what we basically see is that if we make beta L equal to 2 pi by lambda times lambda over 4, right? So we are making it pi over 2, right? So if we do that, we can basically show that the Zn that we have is Z0 squared divided by Z1, right? So we call this impedance inversion or an impedance inverter, right? Because effectively what's happening is that the impedance that you're seeing Z in is now become proportional to 1 over Z1, right? So you are seeing the reciprocal of something proportional to the reciprocal of your impedance. And once again, by controlling Z0, you can transform that Z1 to Zn, and in particular this is very useful. For example, just as an example, let's say Z0, we do the characteristic of 50 ohms, and then Z1 is 25, right? So then we see that what we see is 50 times 50 divided by 25, so we will effectively see a 100 ohm impedance, right? So we can basically get high impedances to low or low impedances to high using this kind of impedance inversion. So it is quite important then, as you can see, to know precisely what the wavelength is in your transmission line, right? So from a modeling perspective, since the transmission line is modeled with the unit inductances and capacitances, then that also means that if you model one short section of the transmission line once, you can reuse it everywhere in your design, because once you have developed a transmission line structure where you know what the width you're using and what spacing you're using, and let's call this the width of the ground, right? So if once you know these details about your transmission line, and then you can design your circuits, just assuming that you will be able to get the Z0 and beta that you target, right? And all simulation tools give you an opportunity to model or use ideal transmission lines if you can provide these coefficients into them. So you can design your circuit, and then when it comes to layout, you just use the model that you've developed, that transmission line of appropriate length, right? So it's a very convenient way of designing at millimeter wave. There will be, I think that in a somewhat justified statement is that transmission line based circuits at millimeter wave can occupy a little bit more area than if we use L's and C's, right? But you can also quite aggressively meander the transmission lines. We will see some examples of that as we continue. One complaint, as I mentioned, is about the fact that T-line based circuits can occupy an increased area, right? So what we see is the development of structures that we call slow wave transmission lines. Okay. And what the idea there is that if we consider the distributed model that we developed, right, there is an unit L dx, there is RDX, where dx is the unit length, right, and then there is the G and C. And this section is repeated, right? And we saw that beta is omega square root L times C, right? So what I would like to do is, since beta is 2 pi over lambda, right? What I am interested in is basically having a very small lambda, right? For which I need to increase beta, right? Which implies that I should basically find some way to increase my LC product, right? And the way that I do that, I mean, is that I take my transmission line, and I'm sort of going to do a side view, but just from an abstract perspective, we can say that what if I just take this, right? And I know that the distributed parameters in the unit cell are this, right? But to each section, I effectively add another capacitance, right, which I'll call C P, right? I increase this capacitance. And so I do that in a distributed fashion. So this section keeps repeating itself, right? So then, yes, I have taken my impedance and dropped it, right? So the impedance has dropped, but my beta has gone up, right? So, I don't, obviously, I can decide to distribute CPE in smaller and smaller sections, or I can do it by, say, for example, taking the transmission line section, right, and then adding a capacitance, and then making another transmission line section, adding a capacitance, or I can break it up and have smaller and smaller sections that are loaded, right? And the trade-off here basically you can show is about the cutoff frequency of the line. The shorter the sections that are, the more you are making this seem like a unit capacitance, the higher frequency up to which your transmission line will behave predictably, right? So a structure that folks will use is that you effectively have a very let's say a wide signal layer. You have a ground layer, and then in the layer below we place basically strips of metal, right? So you can place floating strips, you can place grounded strips. They work, but there have been some papers that have suggested that placing floating strips is lower loss, right? But you can basically place these sort of strips underneath your transmission line, right? And using these kind of strips underneath, right, you can effectively, we are sort of adding capacitances underneath the line in a distributed manner, right? And this approach can effectively end up in increasing the loaded capacitance, and therefore your lambda can be reduced, right? So it can be as much as almost half the wavelength that you would get otherwise without doing this kind of loading, right? And with yeah, so with these kind of structures, the one issue does become that the impedance of this is low, right? Because we have loaded the transmission line. But it is worth noting that, like I said earlier, you are not constrained to a certain impedance on the chip when you're designing. And also many times when you are trying to get, for example, an inductance, right, or a capacitance, then the Z naught is also a parameter that is under my control, right? So if I want, we saw that the inductance that we effectively see is J Z naught tan beta L, right? But here this is completely in my control. So if this drops, yeah, I may have to use a longer L to compensate for that, right? But then effectively I might find that the Z naught doesn't drop as much. So what is happening is that Z naught is dropping, beta is increasing. So you have to compensate overall by picking a different length, right? But these are variables that I can control in order to optimize how big a transmission line that I'm using. So these structures are also quite popular in integrated millimeter wave implementations. So so now that we have the basic building block where we can develop transmission lines with on-chip impedances, let's say ranging from 20 to 100 ohms, right? Let's say that we are able to build something like this, right? Then though this is a high number, right? Probably 70, 80 ohms is when you are for acceptable loss, because in order to get this 100 ohms, you have to make the conductor trace quite thin, right? So effectively, this might be too lossy. So yeah, it might be useful to think about 75 ohms or something like that as a more practical limit of impedances. What kind of circuits that can be built, right? What kind of useful passive circuits can be built? So we'll just talk a little bit about passive circuits that accomplish some useful operations for us, right? One typical application that we use them for is power division, right? And another is to generate power division with a desired phase between outputs, right? This might be that I have this block, right? P in is coming in, and then there is a port 2 and there is a port 3, and I'm putting out a signal to these ports, right? And I might want both of these signals to be in phase. I might want these signals to be in quadrature, or I might want these signals to be anti-phase, right? So I can accomplish all of these things with transmission line circuits or lumped circuits, right? And we'll just start with the transmission line and look at equivalent lumped circuits based on that, based on those transmission line architectures. So this is obviously a very mature area. People have been working on it for several decades, right? So what we will cover is just some very popular circuits or very commonly used circuits, but there are, happy to refer you to textbooks for more detailed circuits, right, or a broader range. So if we think about power division or power dividers, right, this is a very necessary component that we use in all of our systems. So we have port 1 and port 2 and port 3, right? And typically we think of these circuits as reciprocal, right? Which is that if I apply an input to P in, it's going to split into P out 2 and P out 3. But if I'm applying input power to port 2 and port 3, they're going to get combined in port 1 and come out as well. So these circuits are reciprocal, right? And what we would like is that we would want a circuit where I apply an input, right, and none of the power gets dissipated inside my power divider itself, right? And all the power goes to port 2 or port 3. So you could call this lossless, right? And then I might also have a requirement that I'd ideally, let's say that I'm working with a characteristic impedance Z0, right? So whatever is driving this is expecting to see a load impedance of Z0, right? Whatever this is sourcing, for example, is expecting to see a source impedance of Z0. So I'd ideally like my circuits to be matched, right? So that I have, if I terminate them in the right impedances and drive them with the right impedances, right, then I'm able to have the power division that I need. So in 3-port structures, it is not possible to have all 3. 3-port structures, with no anisotropic material. So anisotropic materials are materials that, for example, treat the forward wave differently from the backward wave, right? So in the absence of such materials, we can't get all three, right? So we figure out which of these we can live with, right? And then design our circuits based on that. So just as an example, right, I could make a, let's say that I have a source that is Z naught, right? I can build a circuit that looks like this. This is just a lumped circuit, but just to illustrate the point, right? Right? And then let's say that I'm driving this into Z naught and driving this into Z naught, right? You can basically show that this circuit will divide the power evenly between, so whatever you put in here will evenly split to these two ports, right? And you can show that each of these ports will see Z naught, right, looking in, right? So this is matched. This is reciprocal. So if you apply the inputs, if you apply the outputs, they will combine into the input, right? So that will happen. But this is not lossless. So some power will be dissipated in these resistors, right, when we apply the input. So there are equations on how to design if I want an unequal power split and things like that. But the nice things about this is that this circuit, for example, is quite wideband, right? There is no frequency limitation here. I can, you can buy components that do this kind of power division using these resistors, which are quite wideband, and that works, right? So there is a popular power divider or combiner that we use, which is called the Wilkinson, right? And the reason why we like the Wilkinson is that if we look at these two particular, in this particular case, what we find is that if I call this port 1, port 2, port 3, right? So if I inject some power in port 2, it will come into port 3 in addition to go into port 1, right? But many times what I would like is that I would like my port 2 and port 3 to be isolated from each other, so that if I apply some power, it gets divided, and then this can be a simple application where I might decide that this path may or may not be connected, may be connected to something else, or maybe failing, right? So in all those scenarios, I would not like a change in this path to change the amount of power that's happening in that is there in that path, right? Or if I'm using it as a combiner, if I apply some power here and some power here, if these are different, I don't want this power leaking into the other port causing problems, right? So isolation is useful. So Wilkinson basically, what it does is it provides matching. It provides matching at all ports, at the 3 ports. And then it provides isolation between the between port 2 and port 3, right? Which is useful when we are using it as a power divider or combiner. Wilkinson is a reciprocal circuit, right? So what we so this the assumption is that, let's say I'm again driving it with a port that is Z naught. I'll just represent my port like this, right? This is port 1, and what you effectively have is then So let's say this is a lambda over 4 line, square root of 2 times Z naught, right? And then I have another transmission line, right, which is lambda over 4 square root of 2 times Z naught, right? And this is my port 2, this is my port 3, right? And the key thing is that in between these two ports, I add a resistor that is 2Z naught. Okay. So this is a very popular circuit. You can analyze it, but effectively we can show that if we write out the S parameter matrix for this, right, we get it's matched on all 3 ports. So this is 0, right? It's isolated between S23 and S32. So these are 0, right? And the power gets split between both ports. So this is right. And there are design equations that exist if you would like to do unequal splits, right? So you can do the unequal splits by changing the impedances of these transmission lines, and you can also do N-way Wilkinsons, where you don't have just 2 output ports, you have more than 2 output ports. So design equations exist for that. But one thing to remember here is that this isolation resistor is very important, and it's, you know, its name is given its job away. It is what is providing isolation. So if I provide, for example, an input only into port 2, right? Let's say I apply a certain P2 here, then P2 divided by 2 or minus 3 dB of power will flow into my output port, and the remaining power will get dissipated in my isolation resistor, right? And there will be no power coming out into port 3, okay? So this isolation resistor must be sized to make sure that it can absorb the power that you might get in it. And also there is in practical implementations, it sometimes occurs that these 2 ports are not very close together, right? So then you have to account for that by modeling whatever parasitates that you have over here in order to connect these 2 points together, right? So at millimeter wave, that kind of modeling is important to get performance that that matches this. This is a pretty wideband combiner slash splitter. So it's yeah, it's very widely used for signal distribution at millimeter wave on chip. And you can see that basically the size of this is going to be the order of lambda over 4, right? But one way in which we typically can try to reduce size if we just do want to use transmission line circuits is that instead of using transmission lines that are just straight, we basically meander the transmission line, right? So this is basically, let's say, my CPWG structure, right? So my ground is also going to be like this. This is my sidewall ground, and this is the other sidewall ground, right? Right. So I've now basically implemented a transmission line whose length is basically the total length of this signal trace. You can actually get a pretty good estimate by if your signal trace, of course it has some width, right? So you just go along the center of the signal trace and you get the total length, right? That basically works out very well as a determination of the effective length that you need. There are some good practices in doing these bends, right? So instead of making these bends like that, right, you can, so this is the bend, but each of these bends effectively produces an extra capacitance, right? So what is traditionally done is that when we have the bend, we chamfer it, right? So we make the bend like so, right? So this basically sort of reduces the signal trace width a little bit, which reduces the capacitance, which compensates basically for the fact that the bend has some capacitance, right? So this is a conventional way of doing this. A 45-degree chamfer or a 30-degree chamfer, a 45-degree chamfer, works pretty reasonably as a first order approximation. So we typically, if you have the ground line over here, right? So you just make the ground line also go like this. So this is space. This is the same space, right? And you take it along like that. And then your bend looks like this, right? The inside transmission line, so let's, in this case, if we were to draw the inside transmission line, it would look like so. Right, so that's basically, you can, yeah, there is a bit of asymmetry in the crowding. You can, if you like, do it a little bit even more gradual, where you have the bend as something that looks like this, right? And then you have something that runs even closer to that. In this case, you have to have the same spacing. Right? So you get something that is even more smoother if you're trying to do this, right? Yeah, this approach generally works pretty well to get these kind of meanders. Depends upon the area that you're willing to spend. But EM simulators will of course capture it, right? But we have seen similar approaches work pretty reasonably at the lower millimeter wave frequencies. So if I really want to make this compact, right? If I really want to make it compact, right, I can implement this using inductors and capacitors as well, right? So if we have a LCL pi section, right? We basically can again show that, so this is L, this is C, right? That the Z here is square root of L over C, right? And then if you want this section to have 90-degree shift, right? Which is what lambda over 4 effectively corresponds to, right? You can basically make L is Z naught, Z divided, so this is L over C. L is Z divided by omega naught. So let's say we consider this, right? And C is 1 over Z naught omega naught, right? So if we select these particular values, right, then we find that this basically is a transmission, is similar to a transmission line of impedance Z0 and provides 90-degree phase shift, right? So then I can just implement the lump Wilkinson, right, by making sure that I build something that looks like this. Right? And this approach will work uh, at the particular frequency that we design at. But the challenge, of course, is going to be that we'll have somewhat reduced bandwidth. So if we look over here, you can see the simulated bandwidths for a T-line example, right, which is more wideband compared to a lumped LC example, right, which basically falls off at higher frequencies. You can also see that things are quite well matched across a pretty wide frequency range when we do transmission line based structures. If we consider the 5, 6 and 2, 3 S parameters, they are the isolation S parameters. And what you can see is that isolation is typically more narrow band than the matching, right? So the two, if you decide on the isolation between them as the bandwidth spec, you find that the Wilkinson is effectively operating over a narrower operating range than if you consider only matching, right? And this can be important, particularly in applications where you want to build reconfigurability in your power divider. You want to basically sometimes split power and have both parts operating, or sometimes only one side operating. And again, this kind of approach works. The Wilkinson's isolation is really helpful when you are feeding power, for example, to two blocks. Just as an example, let's say that this is an amplifier and this is an amplifier, right? And I apply some power here, and this amplifier is providing a match when it is enabled, right? And this amplifier is not matched because it's been disabled, right? And in this scenario, the power flows here, right? And then there is some power that flows here, and this is mismatched, so it reflects back and comes back here, right? But this is where the isolation resistor of the Wilkinson absorbs this power, right? So with respect to this amplifier, nothing changed, even though this amplifier has been disabled. When it is enabled, all three ports are matched, everything is fine. When this amplifier is disabled, the Wilkinson helps you isolate, and so you don't see any reflections from this amplifier coming back into your other amplifier that's enabled. Does it make sense? So if we remember the Wilkinson's power split, we can basically see that if you apply a 0-degree signal here, you'll get minus 90 degrees and minus 90 degrees. So both of these signals will be in phase, right? But as I mentioned, we like a signal where we can basically get quadrature phase, for example, right? So we'd like output ports to be 0 degrees or 90 degrees phase difference between them. Right? And there are several circuits that do that, and we will be considering them through the lecture on phase shifters as well, right? But A popular one, for example, is a branch line hybrid. Is a branch line coupler. That's right. And here the idea is that you have one transmission line that is Z naught divided by square root 2 and lambda over 4 long at your frequency of interest. You have a arm here which is Z naught. You have another arm here which ends lambda over 4. This is another arm which is similar to the other one, and then a final arm which is Z naught over square root 2 lambda over 4, right? So with this particular coupler, right? So this we are now looking at what we call 4-port couplers. So port 1, in this case port 2, we'll call this port 3, and this is port 4, right? The interesting thing about this coupler design is that if I terminate this port in Z naught, right, and because you have 4-port couplers, you can have lossless, reciprocal and matched properties, right? So in this kind of coupler, what you effectively see is that if I were to look at the S parameters, right, I see that all 4 ports are matched. I see that port 1 and port 4 are isolated, port 2 and so 1 and 4 are isolated, right? And port 2 and 3 are isolated. So this is port 3 and this, right? And then if I look from port 1 to port 2, there is a quarter wave transmission line, right? So I expect basically 90 degrees of delay between port 1 and port 2. So I get something that is minus j over square root 2, right? And then if I see from port 1 to port 3, I get a minus 1 over root 2, right? And then everything is reciprocal. So you're basically going to get this. And this is minus j over square root 2, right? And you can fill up the rest of the matrix because it's all reciprocal. Right? So if we look here, effectively what's happening is that I am applying a P in, and let's say that corresponds to a V in, right? Or let's call it V1, the input at port 1. Then port 2 is going to be V1. So port 2 is going to be V1 divided by square root 2, and then it's going to be shifted by 90 degrees, right? And if I look at port 3, then that's going to be V1 divided by square root 2 shifted by 180 degrees, right? So there's going to be a phase difference between the two, which is 90 degrees. And what is interesting is that no power comes over here, right, into port 4, provided I terminate it in what is the match resistance, right? I terminate it in Z naught. If I don't terminate it in Z naught, there will be, you can imagine that some power will come here, get reflected, come back here, and then go here and here again, right? So you need to make sure that you are matching that isolation port in the right impedance. But if you do that, you've basically built a power divider which is lossless, right? So if I apply a certain power here, half the power will go here, or half the power will go here, right? And the phase difference between them will be 90 degrees. So I can get quadrature phase using this particular coupler. Again, quite a popular coupler. And again, if you want to build lumped equivalents of it, we've already seen a pi section that gives you lambda over 4 at a frequency and a z naught, right? So you change the values of L in order to get this other section, change these two sections, right? Which are a smaller characteristic impedance. But you can build this using inductors as well, and we will look at implementation that even further reduces that area more. So this was an example of a coupler, but you can a branch line coupler, but you can clearly see that this coupler is going to be quite big, right? Because it's it's got 4 lambda over 4 sections, right? And if I want to get 180 degrees, right? If I want to get 0 degrees and 180 degrees phase difference, again, there are many couplers that do this, right? A popular one that is used in MIMITS is called rat race, and I will show it here, but I'd say that it is less common in integrated implementations because as we will see, it can be quite big, right? So you effectively have sections that are lambda over 4 and 3 lambda over 4 long, right? And we tend to avoid integrating an implementation of this at really high frequencies. But just I also have an example, branch line couplers that have been implemented in on chip, right? And this gives you an example of the sort of insertion loss, right? Even though theoretically it's lossless, you have losses in all the transmission lines, right? And interestingly, you can see here that the loss is reducing as frequency is increasing because the physical length of the transmission lines is dropping because you need a shorter section that is lambda over 4. So you get pretty low insertion loss by the time you get to really high millimeter wave frequencies. This amplitude imbalance is basically talking about how much power difference do you have between port 2 and port 3, right? So they can be pretty close to each other. The phase imbalance is basically talking about how much between 0 and 90 degrees, what kind of split that you have, right? And the area you can see here with all this sort of meandering, it's still quite big, right? 480 by 480 is quite big in an integrated implementation. We will look at other compact quadrature generation approaches, but this to the first order gives you a sense of the areas that we use. So before we maybe talk about rat races and other things, let's actually look at one class of transmission line circuits that we call coupled lines, right? And coupled line we can basically so we can look at a class of circuits that we call coupled line couplers, right? And here the idea is that I'm basically going to have two lines running right next to each other, right? And so I have a port 1, right? And a port 2, right? Let's call this port 3 and port 4, right? So I effectively have a 4-port structure, right? These two lines are running close together. And there's clearly going to be some coupling between these two transmission lines. So if I inject some signal here, I'd expect to see some signal here, some signal here, and some signal here, right? Because these two lines are running together. So what we can actually do is we can control that coupling between these two lines to build several useful circuits, right? So the way that we usually think about these couple line circuits, right, is in terms of their impedance when you drive them in odd mode and even mode, right? So if I were to think about these lines, right? So there is some inductance, right? There is some capacitance that is to ground. There is some capacitance between each other, right? So that's the structure that is there, right? So then what I can basically think about is, let's consider two kinds of excitations, right? One where I'm applying an excitation that is plus at this port and minus at this port. So this is odd mode, right? And when I apply this kind of odd mode excitation, this capacitance doubles, right? So let's call this capacitance Cc. Let's call this capacitance Cg, right? So this capacitance effectively, there's a plane of symmetry and I effectively see 2 Cc. So I can think of my Z in my odd mode, right, as a function. It is basically L over Cg plus 2 times Cc, right? And then if I claim that when I do an even excitation, then if I do an even excitation, then this Cc doesn't appear, right? So my Z even becomes just square root of L over Cg, right? So what we can basically also see is that the odd mode and even mode impedances are a function, or the difference between them is a function of what Cc is. So the odd and even mode impedances are telling us how tightly the lines are coupled or not, right? So what we can define is a coupling ratio, which we call C, which is Z even minus Z odd divided by Z even plus Z odd, okay? And what we can also show is that the characteristic impedance of this coupler when we are exciting a port is going to be, sorry, I've already put this. So let's remove the square. It's Z even times Z odd, right? So so now we can design this for particular objectives, right? Let's say I want, given these equations, let's say I want to have a certain coupling ratio. I can see that I'd like a Z even, which is Z naught divided by square root of 1 plus C by 1 minus C, and the Z odd I should target is Z naught times square root of 1 minus C divided by 1 plus C, right? So let's say that, for example, I want to design a coupler, right, that is going to split power by 3 dB in a 50 ohm system, right? So then I have Z naught as 50, my C as 1 over square root 2, right? And then this basically tells me that I need a couple line structure where the Z even is going to be of the order of 119 ohms and Z odd is going to be of the order of 21 ohms. Okay, so this becomes my objective. So then what I can do is I can create a structure, right, where I have a certain width and I have a certain spacing between them, right? And then I simulate the transmission line by first exciting a port in between these two, right? And calculating what Z odd is, right? And then I can take the same structure, right? And I can simulate it. Okay, let's actually do. I can take the same structure. I can take the same structure and simulate it. By with a even mode excitation where I connect both of these and right, and I'm doing this to the other side as well, right? So I'm both in the odd and even case I'm exciting like that, and in the other side of this I'm taking them together, and I'm basically doing two-port simulations, effectively driving this in odd and even mode and finding what Z even and Z odd is, right? And I see that in order to get a good odd mode impedance that is low, I need to make these lines wide and I need to move them closer together, right? And in order to get a high even mode impedance, I need to make these lines narrow, right? So there is a trade-off in the width and the spacing. Clearly, if I can move my lines closer and closer together, I can get tight coupling, right? And then, it's also just similar to the vertical natural capacitor approach of trying to do tight coupling between different fingers in order to get high capacitances. You have degrees of freedom. You can be creative, right? You can have multiple, so you can connect from here to here and have another parallel edge of this, right? So now basically this port is connected to this. So because we are integrated, we can play tricks like this very easily, right? We can put a VR structure that connects these two, and now this line is coupled very strongly with both the metal traces on the left and the right in order to give you a higher C, right? So why are we doing this? Well, if we build this structure, right, and we make a 90-degree lambda over 4 structure of these coupled lines, right, we basically see that we have built ourselves something that looks exactly like a something that looks exactly like a so if we call this port 1, we call this port 3, we call this port 2, we call this port 4, right? When we have built this structure, we have built ourselves similar to a branch line hybrid. We've built a quadrature structure, right? So now if I terminate, so port 4 is Z naught, right? And so if I were to do the S parameter matrix of this, again all ports are matched, right? Port 1 and 4 is isolated. Ports 2 and 3 are isolated, right? And then you can basically see that this is minus j square root of 1 minus c squared. This is c. This is minus j square root of 1 minus c squared. This is c. This is c minus j square root of 1 minus c squared. So what is this saying? That I can adjust the amount of power. So if I put in a certain amount of power in here, some will be coupled here, some will go through here, and nothing will go here, right? And this is controlled by this C ratio. So if I design C to be 1 over square root 2, for example, then what would happen is that you would get minus 3 dB over here, you'd get minus 3 dB over here, right? But note that this C is 0 degrees, this C is minus 90 degrees, right? So now you have port 2 and port 3 operating as a quadrature split. And this kind of coupler is pretty easy to implement on the chip, right? And we can very tightly and control C, because this is all very high precision metallization. So if you want unequal power splits, or if you want to have a situation, for example, that you want to put in a certain power here, right? And then you want to couple minus 20 dB of the power here, right? And you want the rest of the power to go through here. That's you can accomplish, and then you can put a power sensor here, for example. So then you can know how much power that you are putting into the system. So this kind of circuit is quite often implemented. This is also a directional coupler, because when a wave is coming this way, when you're applying this incident power, some of it is coupled here. But let's say this goes here and there is some mismatch, right? If there is some mismatch, then the signal is going to get reflected, right, and come back here. But none of the reflected signal is going to show up here, right? So this can work as a good sensing point of how much power you are putting in, irrespective of whether the load at the other end is mismatched or not, right? So this kind of coupler is quite useful, both as a coupler where you have an unequal power split, or a coupler where you have an equal power split and you are splitting power in order to get quadrature. And it's quite a wideband coupler, right? And there are techniques to make it more wideband by using multiple sections of these, which are at different lambda over 4, right? And you can even use shorter sections which are not quite lambda over 4 and cascade them. And when you do that, you effectively build yourself a very, very wideband coupler, right? This approach of putting multiple fingers in order to make it more tightly coupled is also quite popular. And this is used right from the days of MIMIC and PCB. So there is a special name for that kind of coupler, which is called a land coupler, right? Where basically instead of having just one line like this, right? So we are doing 2 lines like this in order to couple them, right? So instead, let's say that I create a situation where, so this is line 1, right? So I have this, but then I also have this connected to, so let's just draw out the structure first, right? And right, and what we then have is this structure. That is connected out, and we can basically include fingers of this line as well over here if we want, right? And this. And then do something that looks like this over here. Right? And finally, you can make a connection over here like this, right? So these are all connected together. So you build yourself a very tightly coupled coupler, right? So this also side is connected, yeah. Right? So this kind of coupler, again, integrated implementations exist for this, right? And it actually is more wideband than a branch line hybrid. So you can get a very wideband hybrid quadrature coupler. Yeah. Using this particular circuit. So we looked at these circuits, and you can clearly see that this kind of coupling, you can think of it in terms of a transformer coupling as well, right? So you can basically implement quadrature couplers by building inductors and capacitors. So you build sections, right, that are like so, and then you have a magnetic coupling between them, and you can have an electric coupling between them as well, right? And with this kind of approach, you are effectively building those kind of coupled circuits, right? And you can have again couplers that give you quadrature, right, and even power splits. And you can analyze these kind of circuits in odd and even mode as well. You can clearly see that these CCs, right? So basically, you can figure out that if you want to, for example, decrease your odd mode impedance, you have to increase CC and the coupling between them. And you want to increase your even mode impedance, you have to make sure that this CG to ground is reduced, right? But you can analyze this similar to how we analyze odd mode and even mode circuits for coupled lines. So just as an implementation example over here, you can see that this is at 28 gigahertz, right? And in 150 microns by 150 microns, you can build a quadrature coupler that gives you the 3 dB split, right, with 90-degree difference between the outputs. No, on this, in this, I believe that this is correct, right? So it depends on whether you are emulating a branch line hybrid or a couple line circuit. So in a couple line, the isolation, in a branch line, the isolation is here. In the couple line, the isolation is here, right? So this is a lumped implementation of a branch line. Coming back to the 180-degree split, right? So I'll just sort of mention the rat race because at really high frequencies it is feasible, but effectively you have one transmission line that is square root 2 Z naught and then 3 lambda over 4. And then you have another transmission line which is square root 2 Z naught lambda over 4. Another one which is square root 2 Z naught lambda over 4. And finally another one which is square root 2 Z naught lambda over 4, right? So with this kind of structure, you can basically have port 1 and then this over here is your isolated port, right? This over here is your port 2 and this is port 3. You can see intuitively that this is sort of minus 270 degrees, this is sort of minus 90 degrees, right, from the length of the transmission lines. So you can get a 180-degree phase difference between port 2 and port 3, right? But clearly these are extremely long transmission lines. So building them on chip can be lossy and area intensive, right? So one popular structure at high frequency on chip is, if you're building this using distributed structures, is what is called a Marchand balun, right? And in this structure, you're building it using couple lines, right? So you effectively have two couple line sections. So one like this, and then so this can be an open or a short, right? We'll leave it open here, and then if you round this and if you round this, so this is open or short, it can work, right? And then you basically have this is port 1, this is port 2, and this is port 3, right? So this is lambda over 4 and this is lambda over 4, right? So with this sort of structure within lambda over 2, you can basically get a 0 180 degree line in here, right? And you can analyze this again in even in odd mode, right? But one of the challenges to note here is that again, like as a 3-port structure here, right? You'd like port 2 and 3 to be matched and port 1 to be matched and split signals equally, right? That doesn't work. So what effectively as an example of this, I've provided some papers that give you some design equations on what the S parameters are, right? But if you consider a situation where you are making the coupling coefficient on these transmission lines 1 over square root 3, right? Then what you effectively see is that you'll get if this P in corresponds to a certain B in over here, right? So then you'll basically get B in over square root 2, B in over square root 2, right? Minus B in over square root 2. But the impedance that you see over here, right? So this port will be matched. So port 1 will be matched, right? And port 2, port 3 will effectively be a 6 dB match, right? So you have this trade-off here where you can't match all three. So an ideal balun you would like 0 0 0, right? And then you would like to have 1 over root 2 minus 1 over root 2. You would have 0 over here, right? Because you want isolation between the ports. And then you want 1 over root 2 minus 1 over root 2, right? And 0 over here. So that kind of structure is not feasible, right? So you have to trade off one against the other. But this is typically reasonable because I can design whatever is being loaded by this with the appropriate impedance to live with this, right? So you can build integrated implementations that are quite compact. You can have a transmission line going like this, right, terminated in an open, and then you can have another line running right next to it, which is terminated in a short, for example, and this is one of your outputs, and this is one of your outputs, right? And you are coupling these two lines close together, right? And this is basically a coupling ratio of minus 4.8 dB, something like that, right? If you design it like that, you can basically get this port to be matched, and you can get 0 180 coming out of this particular structure. Right? So this balun from an integrated perspective works very well. Again, you can see that it looks a lot like coupled lines, which it is, right? One of the notes is that when you are trying to build these, when we are trying to do even mode and odd mode impedances, we basically assume the same L in even mode and odd mode. That's not quite right. The L changes between even and odd mode because of the direction of current flow being the same and the opposite. So there is a slight change in L. So usually you get an initial design, but then you have to tinker with it a little bit to make sure that you're getting the right impedances in even and odd mode. and getting the right coupling ratio. So at this point, we have then integrated passive circuits which are able to generate quadrature, which are able to power divide, and which are able to do 0 180 degree difference. This, by the way, works as a reciprocal circuit as well, right? So you can, if you provide plus and minus signal here, they are going to get combined into this particular port as well, right? It's reciprocal. So it can also work as a differential power combiner, which can be a useful circuit in many applications. So we have built quadrature dividers combiners, in-phase dividers combiners, anti-phase dividers and combiners. So we are able to now basically use these building blocks to start building phased arrays. So next we will look at phased array architectures, and then we'll talk about phase shifters and attenuators today. Okay.